Okay, today we're looking at the last bit of the Newton's laws section, the dynamics section, I should say. So part of it, of course, is Newton's laws, and part of it, of course, is this what we're talking about today, and that is free fall. So if an object is in free fall, then as it says here, the only force acting on it is its weight. All right, so gravity pulling down. Now, of course, in real life, it says there it's not strictly true because we have air resistance, but most of our questions that we'll be looking at will be ignoring air resistance. All right, so I mentioned about, of course, that weight's the force on it, so if weight is the force, then what is the acceleration during free fall? All right. Now, it was an interesting start. Aristotle was, I've had to spell his name incorrectly there. That's a bit better. So Aristotle was the first one to come up with some idea, and he said, like, if there's Earth here, then things would fall down to Earth because they had an Earth element, and so they would fall down to Earth because that's where they want to be, where the Earth is. And so then if you had a bigger one, it would fall down faster because it had more Earth element. Now, of course, we know that that's, in real life, that's not necessarily true, that they fall because they have Earth element. So, for example, take a shot put and a feather. The shot put's going to hit the ground first, quite clearly. So Aristotle would have said, oh, the shot put's got more Earth element there, that's why. But nowadays we say, well, the feather's got a lot more air resistance and that affects it more. And so it was Galileo that did some stuff in here. So uh, Galileo, he did some experiments, and from his experiments, he concluded that Aristotle was not correct. And so what Galileo suggested is that all objects fall at the same rate. Right, and that's in your notes there. So, and as I mentioned, light ones appeared to fall slower because of friction or air resistance being greater on them. Now, there's a couple of good videos there that actually show that things fall at the same rate. So there's the NASA one done on the moon, and that's pretty cool. Even though it's a bit blurry, but back in the 1960s, so it's 40 years old plus, more than 40 years old, 50 years old. That video, so thereabouts. So that's pretty good. Dropping a hammer and a feather on the moon, and then also there's a Brian Cox one. So NASA have a massive vacuum chamber, and Brian Cox is dropping a feather, and he drops a bowling ball, I think, in the video. So both of them are pretty cool. So have a look at them. All right. So what is that rate then? All right. So if we have travelling in the vertical direction, some of the forces would be the mass times the acceleration. Now, we've said close to the Earth's surface here, no friction. So if that's the case, that we only have one force, and that's the force of gravity, which of course is weight. Alright, so the weight force will be equal to the mass times the acceleration. Now, the weight force on something, of course, weight, and these are the missing bits in your notes, but weight equals mg. So that means that mg is equal to ma. The m's cancel, so therefore the acceleration is g, acceleration due to gravity. And so that we know is 9.8 Newton per kilogram, gravitational field strength. But, of course, if it's an acceleration, Newton per kilogram is not the right unit in this context. So the right unit in this context for acceleration is metres per second squared. Alright, so Newton per kilo and metres per second squared are equivalent units. So we just need to make sure we use the right one in the right context. Okay, and in this context, because we're talking about acceleration, we need to use metres per second squared. In the weight context, because we're talking about gravity, the gravitational field, we would use 9.8, and that would be Newton per kilogram. All right, so it's the context of that we're using it as to what the units we use. All right, so as it says in your notes there, since the acceleration is constant, it's equal to the gravitational field strength, we can use the constant acceleration formula. All right, what about if we do have air resistance? Well, air resistance, in your notes there, missing bit, so it's opposite to the direction of travel. So if we've got something that's falling down, it will be up. And vice versa, of course. So what we need to do is draw a bit of a diagram. So here we go. This thing's falling down. We've got the weight force pulling it down, and I'll call it AR, air resistance, acting up. Now, air resistance is a little bit more complicated because air resistance is proportional to velocity. And in fact, it's even more complicated than that. It's proportional to the velocity squared. So air resistance, and this is a bit missing in your notes, air resistance increases as velocity increases. All right, so what happens then? Well, if air resistance, if air resistance is increasing, there's going to become a time. So our object will speed up as it falls, and so what that means is that the air resistance will increase. Now, eventually, the air resistance will be equal in size, opposite in direction to the weight. So what we would then have is that the air resistance equals the weight. And this is the missing bits. Then the sum of our forces, which is the weight minus the air resistance, because the size of each of those is the same, is equal to 0. And then, of course, from sum of the forces is mass times acceleration, that tells us that if the force is 0, we get acceleration equals 0. So, and if acceleration is equal to 0, our velocity must be constant. All right, and so we get to what we call terminal velocity. So this velocity is called terminal velocity. All right, and terminal velocity happens quite a bit. So the feather that I talked about before, it reaches terminal velocity. All right, gets a lot of air resistance, and eventually it just floats down. So another thing is a parachute. You reach a terminal velocity on with a parachute. Unfortunately, because the parachute and its big air resistance, that velocity is relatively low, so you can land on the ground. All right, there's a whole bunch of stuff. Table tennis ball's another one. If you try and kill someone by throwing a table tennis ball, you'll find it doesn't go very fast, so it's not going to be very successful. Not that I suggest you should be killing people. That's against the law. So don't go doing that. All right, so a couple of points to note then about our free fall that we were talking about. All right, so no friction, so no air resistance. So it says there, when a body's thrown up, it comes to rest momentarily at the top of the path. All right, so here we are at the ground, got a ball or something, and we throw it up, and that ball will go up, and then it will come back down. So it's changing direction, so it'll be slowing down, momentarily stopped, and then back down. So if it's momentarily, the velocity here equals 0. Momentarily, doesn't matter that it's momentarily, but we can actually use that as a piece of information that's useful to us. Right, and of course the acceleration is equal to g, and of course if air resistance is equal to 0, acceleration is equal to g for all masses. All right, so let's do a couple of examples. Okay, so here we got a rock of mass 5 kilos, dropped from a height of 45, starts at rest, air resistance is 0, G is 9.8. Alright, so first bit, what is its acceleration 2 seconds after it's released? Here it's saying air resistance is 0, so if air resistance is 0, we're talking about free fall. And for free fall, the acceleration is equal to g, which is equal to 9.8. Alright, so it doesn't matter whether it's 1, 2, 5, 10, 15 seconds into the motion, it stays the same because there's no air resistance. Alright, the next question is how fast will it be going? Alright, so it's here, there's the ground there, that's 45 metres all the way down, so that's 45 metres. And if we drop it, then it falls down, and then what we want to know is how fast it's going to be going there, and what we know is that the time here between there and there is equal to 2 seconds. Alright, so if it's dropped, then its velocity, initial velocity, would be equal to 0. Alright, what do we know? Well, of course we know we want V. We know U is equal to 0. We know the time is 2. And we know the acceleration is 9.8. Alright, so simply if we're going to use V equals U plus AT, then we'll get 0 plus 9.8 times 2, which is 19.6 metres per second. Alright, so just using constant acceleration formula. Alright, now part C. Part C, how long will it take to reach the ground? Alright, so remember it starts up here, the ground's down here, and as we said, that distance between there and there is 45 metres, so it's got to travel 45 metres. How long is time? What else do we know? We know that u is 0. So we know u is 0 because we let it go. We know a is 9.8, and we know that x is 45. Alright, so the formula that we're going to need is the one that's got those four things in it. So the one without v, so x equals ut plus a half at squared. So 45 equals 0t plus a half times 9.8 times t squared. So 45 equals 4.9 t squared. Divide both sides by 4.9, you get that t squared is 9.18, and then square root that, you get 3.03 seconds. Alright, so again, we're just using constant acceleration formula here. Alright, so the next question here then is how fast is it going just before, on the instant before it hits the ground? So again, we know that's 45 metres. We know u equals 0, and we want to know what v is down here. Alright, so what do we know? V is what we're after. U we know is 0. A is 9.8. And x is 45. So we want the one that's got those in it. And I believe that would be v squared equals u squared plus 2ax. So v squared is 0 squared plus 2 times 9.8 times 45. When we stick that in our calculator, we get 822. And so to get v, because that's v squared, remember, we need to square root that, and we get 29.7 metres per second. All right. So that's that. The next part of the question asks us about what if there was some air resistance. So what would the acceleration be if the air resistance was 3 newtons? So again, this is not a realistic thing, because remember, as I said, air resistance changes as the thing speeds up. But nonetheless, we'll look at that. So we're really looking at some of the forces, being the mass times the acceleration. So we got our weight force acting down, minus the 3 resistance, mass is 5, acceleration is what we're trying to find out. So the weight is 5 times 9.8, minus 3 equals 5 times A. And so the left-hand side, when you work that out on your calculator, you get 46 is 5A. And so the acceleration is 9.2 metres per second squared. A little bit less than what it was without resistance. All right, that's example 1. Example 2, let's have a look at example 2. Okay, so the initial speed of a stone projected vertically upwards is 21 metres per second. What is the maximum height reached? So here we are on the ground. Here's our stone. We shoot it up there, it goes up, and then it will come back down. So we're wanting to know this distance here. All right, now, in the previous question, everything was all in the same direction on the way down, so you didn't have to worry too much about directions. But this one, we're throwing it up, gravity's pulling it down, so we need to assign a direction as positive. Now, I always use up as positive, and I just stick to that. I find that is less confusing for me. Up's positive, down's negative, and just stay with that I just stay with that convention all the time. So My initial speed is what I'm after. I know my acceleration is due to gravity, and because acceleration will be down, that's where the negative comes in. That's also going to slow the thing down when we chuck it up. X, the maximum height, is what we're after. The question is, what else do we know? Now, remember back, one of the notes was about the maximum height, that momentarily it's at rest. So, we need to use v squared equals u squared plus 2ax. Put in our information that we've got. So 0 squared equals 21 squared plus 2 times negative 9.8 times x. When we figure a few of those things out, so this bit's going to come out negative, so I'm going to do two things at once. I'm going to multiply that together and shove it over the other side, and so when I do that I get 19.6x is equal to 441. Divide both sides by 19.6 and we get 22.5 metres. This is how high it is. Alright, how long does it take to reach the highest point and what is the total time in the air? That's the next part, so let's go to the next page. Alright, so we can look at the same kind of thing. So how long does it take to get to here? So this time we're after time. Using up as positive again. So u is 21, v is 0 again, acceleration is negative 9.8, and the time is what we're after. So v equals u plus at would be the formula we're after. So 0 equals 21 plus negative 9.8t. So 9.8t is equal to 21. Divide both sides by 9.8 and you get 2.14 seconds. Alright, so that's the time to the highest point. Now, I've just noticed that in my notes I haven't got the total time. So, if it takes 2.14 seconds to go up to here, and then it's going to come back down, again, the same thing that's operating on it is gravity. So it's only gravity, it's only acceleration due to gravity that affects it. So the second half is just going to be a mirror image of this. So it's going to start at 21, slow down to 0, and here it's going to start at 0 and speed up to 21. So the time that it takes on the way down is the same as the time it took on the way up. So what that then means is my total time equals 2 times 2.14 seconds, which is 4.28 seconds. All right, the last bit. All right, this one. How long is the stone more than 10 metres above the ground? So here's our ground, and here's our stone. It goes up and then it comes back down. And let's say, for example, this is the 10 metre level. So it goes up, passes 10 metres, goes a bit further, and then comes back down, because of course, remember the total height was 22.5 metres. All right, so again, let's use up as positive. So 10 metres above the ground. Let's have a look. Let's say, all right, so my initial, I'm coming right from the start here, so my initial speed is 21. The distance that I'm interested in is 10 metres. The acceleration is negative 9.8 as usual. And the question asks, how long? So that's time. So time equals. So x equals ut plus a half at squared. So 10 equals 21t minus, or plus a half times minus 9.8 times t squared. Alright, so if I neaten that up, that's negative 4.9. Bring it over the other side, so it's 4.9t squared minus 21t plus 10 equals 0. Alright, so this question you actually would not be expected to be able to do because you need to use quadratic formula or CAS, and that's really beyond what we're doing. But anyway, so if you use solve on your CAS calculators, what you find is that there's a time t equals 0.546 and another time of 3.740. Now, of course, that makes sense because this was from the start. This is when we chucked it to begin with. So 0.546 after it was chucked, it goes past 10 metres on the way up. And then 3.74 seconds after it was chucked, it passes 10 metres on the way down. So the time above 10 metres is this bit up here. So to find that, we just need to subtract. So 3.740 minus 0.546, and that would be 3.194 seconds that it's above 10 metres in its journey. All right. Righto, there's your two examples. Have a look at those videos that I mentioned, particularly the NASA one and the Brian Cox one. They're pretty cool. And you've got a problem set. And also, it reminds you that you're also going to have a test at this point. That's really the main gist of the test is the dynamics. So it's the Newton's law and the free fall. That's what it will be about. However, you will need to, as a matter of course, as you saw in this last one, the free fall, we use the constant acceleration formula. So there'll be certain things you will need to use as a tool for that, but they're not specifically tested. It's the Newton's laws and the free fall that's the focus. All right, again, as usual, anything you're not sure of, make sure you ask.